Hey everyone, if you've got a chemistry exam coming up, you are in the right place. We are going to do a complete breakdown of everything you need to know about ionic compounds so you can walk into that test feeling totally confident and prepared. Let's jump right in.
So, what's the big secret behind ionic compounds? Honestly, it's super simple. You've got a metal atom that gives away an electron and a nonmetal atom that takes it. Suddenly, one's positive, the other's negative. And what do opposites do? They attract. They just stick together like tiny, powerful magnets. That's it. That's the core idea we're going to build on today.
So, here's our game plan. We're going to start with the players, the ions themselves. Then we'll look at the bond, which is that magnetic attraction. After that, we'll meet the teams, these special groups called polyatomic ions. From there, we'll learn the rules for writing their formulas, and finally, how to give them their proper names. See? Each step builds right on the last one. Let's get started.
Okay, first things first. Let's meet the main characters in this story, the ions. You really have to get what they are and why they form, because it's the foundation for everything else. So you might be wondering, why do atoms even bother giving and taking electrons? Well, it all comes down to something called the octet rule. Basically, atoms just want to be stable. They're happiest when they have a full outer shell with 8 valence electrons. You know, they want to be like the cool kids of the periodic table, the noble gases. That's their goal. And this whole drive for stability is what kicks off the entire process.
All right, let's break down the two types of players we have here. On the left, we've got cations. These guys come from metals. Now, to get stable, they lose electrons. And think about it. If you lose a negative electron, what's left behind? A positive charge. That's exactly why sodium, Na, becomes the positive Na+ ion. Then, on the right, we have anions, which come from nonmetals. They're already super close to having a full shell, so they gain electrons. And of course, gaining a negative electron gives them a negative charge. That's how chlorine, Cl, becomes the Cl- ion. It's just that simple. Lose a negative, you become positive. Gain a negative, you become negative.
And get this, there's an awesome shortcut you can use. The periodic table is basically a cheat sheet for these charges. Metals in group 1, they always lose 1 electron, so they form a 1+ charge. Group 2 metals lose 2, so they form a 2+ charge. And on the flip side, the nonmetals in group 17 just need 1 electron, so they form a 1- charge, and group 16 needs 2, so they form a 2- charge. It's a super reliable pattern, and knowing it will save you so much time.
Okay, so we've got our positive players and our negative players. Now let's talk about the force that actually pulls them together. Let's talk about the ionic bond.
Now here's a really important point. An ionic bond isn't a physical thing, like a tiny rope tying 2 atoms together. Nope, it's an invisible force. The official name is electrostatic force, which is really just fancy science speak for the fact that positive and negative charges are powerfully attracted to each other. It's just like we said before, a strong, invisible magnetic pull between opposites.
And this super strong pull has real effects you can actually see. First, it pulls all those ions into a really tight, organized pattern we call a crystal. Just picture a grain of table salt. That's what we're talking about. Second, because that attraction is so strong, it takes a ton of heat to break them apart, which means they have really high melting points. And finally, and this is a big one for your exam, solid salt can't conduct electricity because the ions are locked in place. But if you melt it or dissolve it in water, those ions are suddenly free to move around, and that movement of charge is electricity. All right, you've mastered single ions. Let's level things up a bit. Sometimes atoms get together in groups that act like one single unit with one single charge. Let's meet these teams.
The absolute best way to think about polyatomic ions is to see them as a team. It's a group of atoms that are bonded together so tightly they act like one piece. The most important thing to remember is the entire team has one overall charge, and you never, ever break the team apart when you're writing formulas. They stick together no matter what.
And here they are, the star players you absolutely have to know for your test. Seriously, treat this slide like a set of flashcards. You need to know the name, the formula, and the charge for every single one. We have ammonium, which is the only common positive one here. Then there's nitrate, hydroxide, carbonate, sulfate, and phosphate. Just trust me, memorizing these is one of the biggest keys to getting a great grade.
Now, here's a little memory trick that's a total lifesaver. When you see 2 of these ions that sound almost the same, like sulfate and sulfite, just look at the ending. The ite version always has 1 less oxygen atom than its ate partner. So look at the example. Sulfate is SO4, but sulfite is SO3. The ite is light on oxygen. It's a simple little rule that works every time.
All right, we have our players, and we have our teams. Now it's time to learn the rules of the game, how to put them together to build a proper chemical formula.
Okay, listen up, because this is the golden rule. The number one most important thing to remember is this. Ionic compounds are neutral. They have no charge. That means all the positive charges from your cations and all the negative charges from your anions have to perfectly cancel each other out. The final grand total has to be 0 every single time. That's our goal.
So how do we guarantee that we get to 0? Well, there's a fantastic little shortcut called the crisscross method. Let's try with aluminum, which has a 3+ charge, and oxygen with a 2- charge. It's easy. You just take the number from the aluminum's charge, the 3, and make it the subscript for oxygen. Then you take the number from oxygen's charge, the 2, and make it the subscript for aluminum. Just ignore the plus and minus signs, and boom, Al2O3. It's a super fast way to get the ratio right.
Okay, but what happens when you crisscross with one of our polyatomic teams? Let's say we combine magnesium, Mg2+, with the nitrate team, NO3-. When we crisscross, that 2 from the magnesium needs to apply to the entire nitrate team. So to show that, you have to put the nitrate in parentheses before you write the subscript 2. This tells us we need 2 whole nitrate teams to balance 1 magnesium. If you forget the parentheses, you get MgNO3 which is totally wrong and means something completely different.
We've built the formulas. We are in the home stretch. The very last step is learning the rules for giving each compound its correct official name. Let's break it down.
This little table makes it so easy. Let's just walk through it. First up, the simple stuff, a metal and a nonmetal, like NaCl. You just say the metal's name, sodium, and then change the nonmetal's ending to "ide." So chlorine becomes chloride, sodium chloride. Done. Next, for those trickier transition metals, you have to use a Roman numeral to say what its charge is. In FaCl2, we have 2 chlorides, and each one is 1-. So to balance that, the iron must be 2+. That makes it iron Roman numeral 2 chloride. And finally, if there's a polyatomic ion involved, you just name the metal and then you name the team. Don't change any endings. So Na2CO3 is just sodium carbonate. That's it.
And that's it. That's the whole shebang. We covered the entire journey. We started with why ions even form in the first place, that quest for stability. We met the players and the teams. Then we learned how to use their charges to build formulas. And finally, how to give them their proper names. You've connected all the dots. You've got this. You are ready for your exam.
So I'll leave you with the final little puzzle to chew on, and it pulls together a really key idea from today. Why is it that salt water can conduct electricity, but solid salt by itself can't, and pure water by itself can't either? Think about what needs to be in that water, and more importantly, what it needs to be able to do. Good luck with your studies.